Hello, this is Nolan Hartwick, and I'm conducting the review session for the Trilogy Data Science program for December 18th. Tonight, I plan to recover argument packing and unpacking, along with decorator functions and syntax, along with the functools module, along with introducing you guys to MapReduce. So should be fun. All right. So revisiting packing and unpacking. If you guys remember, so let's say we have some collection of objects. We can, say, invoke this format method by passing in objects directly, by indexing the objects directly. And we can do that pretty easily, but it's also kind of ugly. Instead of doing that, we can use the star syntax to unpack our iterable and pass each of the objects in as a parameter itself. So this line and this line are effectively equivalent. And this line and this line are effectively equivalent. This star operator is going to take each value in that list and put it inside of the format call. So just quickly verify that that works. Hooray! We get some nice, pretty formatted strings, and they're the same both times. How does this work, though? Because you may not be noticing it first, but this format method is kind of weird. It can accept any number of arguments, which is different than any of the functions we have asked you to define so far. In fact, we haven't told you guys how to do it yet. I'm going to tell you how to do it tonight. And it uses a syntax very similar to what you're seeing here with this star operator. So normally when you're defining a function, you can, before I move on, does anyone have any questions about the star operator and unpacking? This is a review, so. Okay, perfect. So when you're defining a function, normally you would just say, I want an average and I pass in a values object. And then you can compute the average on the values, but I don't want to do that. What I want to do is pass in each value as a separate argument and make it so that this function can accept any number of arguments. And the way that you do that, the way that you signify that this function can accept any number of arguments, is to add the star before the argument name. And what this does is basically take all of the positional arguments that get passed to the function, pack them up into a tuple, and inside of your function, you can treat that argument as if it's a tuple. So I'm trying to compute the average. The first thing that I do is check to make sure some number of values was passed. If nothing was passed, then I return none. Otherwise, I sum across all my values and divide by the length to compute the average. And this is just me using the function a few times. So let's just run this real quick. So here that you can see that I'm passing in two separate arguments, and they end up getting packaged together in my function. So this values is going to end up containing a tuple, or sorry, this values becomes a tuple containing 5 and 10. And that's kind of how this, you can have any number of arguments. That's how this, you can have any number of arguments things works. And you really can have any number. Like here I'm defining a bunch of numbers and I'm passing all of those numbers in using the star syntax from before. And it correctly computes the average, which is 150.125 apparently. You don't have to stop there though. You can mix this star syntax with normal positional arguments. So I can have 5, 6, 7, and then all of those arguments that I pass in. And this lets me create this function that can just kind of accept any number of values, however you want to throw them at it, basically. And the new average of 567067899 ... is 110. So once again, this star syntax, when you have an argument in a function with the star in front of it, what that communicates to Python is that all of the extra positional arguments will get wrapped up and passed as a tuple object. Does this make sense? Any questions on this? Okay, moving on.
So
So
even
that's
if the
how.
even if the argument is a list or a tuple, it doesn't matter. It's going to still accept it, right? That's what it shows over here.
So keep in mind that here I'm unpacking that list and passing each of the items in the list.
Oh, it's
So
how are you unpacking it?
with the star operator,
Oh,
just like
okay.
up here with format,
Mm-hmm.
I'm unpacking the names.
Okay, got it.
So that syntax earlier is equivalent to basically saying this. Not quite.
No, there is one square bracket in the beginning. Yeah.
Yeah. And what I'm really just trying to show off here is that you can have, if you want to define a function and you want it to have a variable number of arguments, potentially an unlimited number of arguments, you can do that. And this is how.
Okay.
Specifically, this is how you have an unlimited number of positional arguments. But there's another type of argument. If you guys remember correctly, there are these things called keyword arguments. And here I'm using keyword arguments along with the format method and this dictionary. So the format method is going to look through here and find this keyword youngest, and it's going to look for youngest in its arguments. So it's going to say youngest equals names of youngest. So Nolan gets inserted there. And oldest is Roland. Oldest equals Roland, and Roland gets inserted here. I'm creating the same strings as before. This is basically the same thing as was going on up here, except now I'm using keyword arguments to pass my values. And if you remember, we can also unpack dictionaries. It doesn't work quite the same way as lists, but when you have this double star syntax, what that does is take each of the key value pairs in the dictionary and pass each of them as keyword argument pairs. So this line is not quite the same as this line, but I think you guys get the idea. So when I do the star names, it's going to take each of these items and pass them in kind of like how I'm manually doing it here. But it's much more convenient because you can just do the star. You guys follow me here?
Mm-hmm.
Cool. And just like the syntax for defining an unlimited number of positional arguments is kind of the same as unpacking, defining an unlimited number of keyword arguments works basically the same way as unpacking dictionaries. You simply do star your variable name, and then all of the extra keyword arguments will get tossed into kargs as a dictionary object. So what does this function do? This function has any number of positional arguments, any number of keyword arguments, and it prints a formatted string which restates the arguments. It's not a particularly complicated function, but we can go ahead and run it by running this cell. Logger 0, 1, name equals Nolan. We can see that args is a tuple containing 0 and 1, and kargs becomes a dictionary containing name equals Nolan. We can do it with no arguments at all, in which case we get an empty tuple and an empty dictionary. We can do it with even more keyword arguments, in which case we just get a bigger dictionary. So if you want any number of positional arguments, you use star and then your variable name. If you want any number of keyword arguments, you do star star and then your variable name. Does that make sense?
Yes.
Pretty straightforward, right? So I introduced you guys to that both because it comes up every now and then, and I'm planning to use it later tonight with decorators. All right. So what is a decorator? You guys have actually seen them before. If I go look at, here, I think. Yeah. Whenever you see this @ symbol, what that's doing is invoking a decorator. You guys have been using decorators since we first introduced you to Flask. But what is a decorator? Well, a decorator is a function that accepts another function as an argument and returns a function. So this is just a really simple decorator that doesn't really do much of anything at all. And you know it's a decorator because it accepts a function as an argument and it returns a function object. So how does this work? Well, we start by defining our decorator. Inside of that, we can define a new function that we plan to return. In this case, I named it ret. My new function that I'm returning is going to have any number of arguments and any number of keyword arguments. It's going to print, and it's going to make it so that whenever you call this returned function, it prints, I am decorating a function, and then it calls and returns by passing the parameters to the original function. So it almost doesn't do anything at all, but it basically makes it so that functions decorated with this decorator have a print statement before they're called. So let's just quickly define that, and let's use it. So just like I showed you before, you can invoke a decorator by using this @ symbol, followed by the decorator name, and then immediately following that with your function definition. In this case, my function is computing an average for some list of values. Note that this is not the same average function as I showed you guys before. This is a new function. So when we call, instead of getting this exact function, what we're actually getting is this function. So average of range 5 is going to go in here. It'll pass range 5 in as an argument. It'll say, I am decorating a function. And then it passes range 5 to the original function, which is average. This can be made even more explicit by explicitly calling the decorator. This cell and this cell are exactly equivalent, or close enough anyway. They're virtually equivalent. So what's happening here? I'm defining a function. I am passing that function as an argument to my identity decor, which is a decorator function. And I'm naming the result average. As a result, I can call it and do all the normal things, and it behaves exactly the same way. This @ symbol is basically just applying your decorator to the function that comes below it. Does that make sense to everyone?
No, not really. So when you say the last print statement, average of range, is it calling the average function or is it calling the left-hand assignment thing that you written down just after the function definition?
So when this average right here
Yeah.
is the same as this average,
Okay.
which is the result of calling my decorator function on this average. So this is my decorator function. It accepted that average function as an argument,
Mhm.
and it returned a new function which calls the average argument inside of it.
I see.
I'm basically wrapping the average argument.
Okay.
Does that make sense?
Yeah.
And this same thing is happening kind of in the background in your Flask applications.
Okay.
The Flask is taking your function and wrapping it with some extra logic to make it work as a web endpoint.
Okay.
You don't need to understand the full logic of it all, but that's how it's working. This app.root is returning a function, and names is being passed to that function. So this identity decker is a function. Average is also a function which is being passed to the identity decker. This is, I know that this is complicated. We're venturing into an area of computer science called higher order functions. A higher order function is any function that accepts another function as an argument. And they're very powerful and very abstract and kind of hard to think about, but they're also very handy if you can get used to working with them. All right. Any other quick questions before I move on? Okay. So this decorator isn't great though, because in my original average, I have this nice doc string that tells me what the function does. But the decorated function loses that functionality. It's now getting the doc string from here, which is just not very useful. How can we fix that? Well, Python makes it easy. It has a built-in library package called functools. And one of the functions inside of functools is called wraps, which is going to make it really easy to make nice looking decoratives. So the wraps function is going to preserve the doc string of the original function. And that's what the goal is. So that when you decorate the average function with whatever functionality you want to add to it, you don't lose the doc string that tells you that you are in fact calling the average function. So here I'm importing functools, and I'm also importing JSON, which is a library you guys should be familiar with. But functools is new. And I'm defining a new decorator called JSON logger, which is going to, given some function, it's basically going to add logging to that function so that whenever you call the function, it is going to print a JSON formatted string that tells you what arguments were passed to the function. So you can see that here. I take all the arguments and all the keyword arguments, and I format them in this dictionary, and then pass that to JSON to convert it to a string. That's what this decorator does. But the key thing that I want to show you guys is this functools.wraps. You see, this is also a decorator. I'm using a decorator inside of a decorator. It's meh, what else? And you're gonna see this type of thing a lot. Basically, whenever you define a decorator, you should be using wraps or some similar library functionality to fix the help statements, the doc strings of the function of the method you generate. So let's just quickly run this and run an example. Just like before, this is the same average function, except now we're decorating it with the JSON logger. And you can see that when I call average with a list of arguments, it's going to pass in, it's going to produce this JSON formatted string with the name of the function and all of the arguments that I passed to it. I'm also going to go ahead and invoke the docstring by calling help. And you can see that the original docstring is still present, which is kind of nice. We can add functionality to the functions that we define while preserving the information in the docstrings that make it easy to read about them and think about them. Does anyone have any questions about the wraps function? Does everyone understand why we use it or where you would use it?
Yes.
Cool. That's not the only cool thing in FuncTools though. So this, okay. This is the Fibonacci function, and this is from a couple of activities ago. Actually, I think I showed it to you guys last week too. And it's going to compute the nth term of the Fibonacci sequence. If you don't know what the Fibonacci sequence is, I don't know, look it up. Basically, or just, I don't know, look at the equations here and you can figure it out. Now, one of the dangers of this function is that it's very inefficient. It's incredibly inefficient. If you, like fib3 takes almost no time at all. But if I do fib30, it's probably going to take almost a second. Or many seconds. If I do fib32, it's probably going to take like 15 seconds. Or longer. So, all right, there we go. This function is very inefficient. And it's inefficient because I implemented it recursively, and it's doing a lot of the same function calls over and over and over. So I can show you guys that by just using that same JSON logger from before. And when I call this with fib equals 5, where am I? Here. So fib of 5 produces this really long call table. This is all of the times this Fibonacci function got called when I called fib of 5. And it happens because fib of 5 results in me calling fib of 3 and fib of 4. Fib of 4 results in me calling fib of 3 and fib of 2. And you get this nested pyramid of function calls, and it's very inefficient. We can make it very efficient using this other FuncTools method, this other FuncTools decorator called the LRU cache. For those who aren't aware, a cache is a temporary storage of data so that you do not have to repeat the access calls or computations that you had to earlier. So in this case, what this decorator does is say, whenever I call the fib function, save the results. And whenever I call the fib function with the same parameters, I can just return the result that I computed earlier. And now fib is going to be very efficient. Before, doing fib of 32 took like 10 seconds. Now I can do fib 300 in a fraction of a second. This is an example of the type of power that you can get with decorators. And it's also a specific example of one of the FuncTools methods. Just by adding this line of code, I turned this function from being incredibly inefficient to taking fractions of a second to do very large calculations.
That max size 128.
Yeah.
What is it? It's like,
so the cache is restricted in size. The max size is telling you how many of the most recent calls to store. So in the background, this FuncTools LRU cache decorator is creating a storage table that's storing the function call results. It will store at most 128 results.
okay. We can increase the size to any value, right?
Pretty much, yeah.
Okay, got it. Thanks.
It just costs more memory. Yeah. You guys probably aren't going to run into situations where you want to use this in your homeworks. It's more of something, it's only really something you would do when you have a recursive function or a function that is fetching data and it takes a long time to fetch the data. But it's very handy when it comes up. For example, in this case, with computing Fibonacci numbers, it dramatically streamlines the process. Any other questions before we move on?
No.
Okay. So the next thing from FuncTools that I wanted to show off is this decorator called total ordering. Total ordering is going to make it really easy whenever you guys are defining classes. If you want to be able to compare instances of the class, if you want to be able to say, is this object less than or equal to some other object, let's say, like is 2 less than 5? In that case, you don't need to do this because it's already implemented. But if you're defining your own objects, they do not have comparisons by default. You have to add them. And rather than adding all possible comparisons, of which there are like 8, you have equals, less than or equal to, less than, greater than or equal to, and not equal to, and I think that's about it. But so 6. Instead of having to define 6, you only need to define 2, equals and less than. And from these 2 functions, the total ordering decorator is going to just, it's going to infer what all of the other relationships are, because it can figure out that if this object is not less than the other object, then it's greater than or equal to it, and so on and so forth. In terms of what this object is, this is me reusing code from a previous review session. This is a stack object, which I can describe to you guys, or you can watch the old video, or you can just read the comments. And all I changed here is that I added equals and less than, which are other magic methods in Python that I did not show you guys last time, but I'm showing them to you now. Because I implemented those, I can now do, oh, it's gone. It's right here. Okay, well, switch back. Perfect. Because I'm using the total ordering and I defined these 2 methods, I can now do all of the comparison operations. I can do equals, I can do less thans, I can do greater thans, and any other combination. So just to show that off, I create 2 different stacks. This stack, which is from top to bottom, is 0, 1, or sorry, from bottom to top is 0, 1, 2, 3. So 3 is on top of the stack. And the second stack, which is 0, 1, 2, 2 is on top of the stack. We briefly print them, and then we ask, are they equal? No, they're not. Is B less than or equal to A? Yes, if you iterate through the values, you will notice that 2 is less than 3. Done. And in this case, it's helpful to, I really should have documented what these mean, but oh well. There should be doc strings here telling you what less than or equal to means, because you can define them however you want for your own objects. In my case, I'm going through the stack and seeing which one has the lowest object first, basically. And in tight cases, it's about length. Is B greater than A? Yes. B is less than or equal to A. B is not greater than A. If I add 3 on top of B, then it becomes the same stack. And when I ask if they're equal, they are in fact equal. So I know this is a lot to take in. I'm relying on the fact that you guys have seen almost all of this code before. This is the only new code. And all I really want you to get out of this is that FuncTools has this cool total ordering decorator that lets you define, that lets you make your custom objects orderable. The other thing I want you to get out of this is that decorators don't only have to be used with functions. Decorators can also be used to add functionality to classes. So, any questions before I move on?
Can you explain one more time about the ordering?
So this total ordering decorator, which you can read more about at the FuncTools documentation page, which I linked in the notebook, lets you make your custom objects orderable. So if I don't have this, all right, then when I come down here, I'm going to be able to do equals equals because I defined equals for this object. I'm going to be able to do less than because I defined less than, LT, but I'm not going to be able to do greater than. That will not be defined. Did I fuck up? Execute, execute. Oh, that's cool. How does that work?
That's funny.
Huh. Okay. I guess Python 3. Huh. All right. So that's so weird. What happens if I change this? Cool. All right. So
Then we don't
apparently-
need to use ordering, right?
No, you don't. Apparently, Python just figures it out once you define enough. Once you define one of them, I guess Python just does it implicitly. If I remove this, it should fail. Yeah. That's
Got
cool.
it. Yeah, that's cool. Yeah.
But yeah, apparently you don't need total ordering. My bad. It does do what it says, and I suspect Python is using total ordering in the background. But
Yeah, so which means that ordering was like a function that was used in the previous versions of Python, right?
yeah,
Yeah.
before they somehow baked it in as basic functionality somehow.
And now I guess it's inbuilt now.
Yeah. All right. We're about halfway through. I have more content to go over, but if any of you have questions related to this content or other content, let me know. Do you guys want to ask questions, or do you want me to continue doing stuff?
I'm good.
Any response?
I'm good.
Anyone have any preference?
It's fine to keep going for me.
Okay. in that case, just really quickly going back and revisiting this, even though functools.totalOrdering apparently isn't needed in Python 3, you can decorate classes, and it does work. It's just, this is a bad example, and I apologize for that. So moving on, what's the next functools function that's pretty handy? Well, here's one to introduce you guys to. It's called partial. And partial is going to let you take any function and basically give it new default parameters. So let's quickly run this. Here I call functools.partial. I pass in the print function, except now I'm passing it with the keyword argument end equals new line, new line. By default, end is set to be equal to new line. I'm basically overwriting it in my new function, which is I have called new print. So new print 4 prints 4, new line, new line. New print 4 prints 4, new line, new line. Whereas if I just called print of 4, you would see that it just prints 4, new line, 4, new line. I have basically changed the default argument, which is often quite handy. Instead of having to continuously retype the same or similar function calls over and over, you can create a partial that does most of the work for you. This partial doesn't only do that, it has a bit of extra functionality as well. So here I'm using it to set new defaults for the Fibonacci function. Instead of being rooted with 0 and 1, I'm rooting it with 4 and 1. As a result, I can call new fib of 9 and get an answer of 50. I can also, so this gets back to the extra functionality. When you define a partial function using functools.partial, your function will have some extra attributes. Specifically, it will have the keywords attribute, the args attribute, and the func attribute. Keywords is going to tell you which keywords you have defined as part of your partial function. And these keywords will be passed to the function whenever you call your new function. The args is going to give you the list of all the positional arguments that you have defined as default, basically. And those are constantly being passed whenever you call your new function. The func object lets you access the original base function, which is sometimes quite handy if you either intentionally or unintentionally override a function. For example, if I did print equals functools.partial print some stuff. And whenever I call print from now on, let's do this in a new cell. If I just call print, it's going to print some stuff. If I call print 5, it's going to print some stuff and 5. This isn't very desirable, but fortunately, I can access the original function by saying print.func. And you can do this whenever you define a partial function. So just really quickly, so that I don't break anything, I want my original print function back. Done. And comment this out. And comment this out. Any questions on the partial function? It's pretty straightforward, right? Just lets you set default arguments so that you don't have to constantly type them in. Yeah, well, Any questions on any of the func_tools functionality that I've shown you guys before I move on? Okay. So I thought I'd introduce you guys tonight to a programming style called MapReduce. This programming style is going to become, you guys are going to be learning it in class. I'm not exactly sure when, but at some point in the next few weeks, and potentially even when we get back from, immediately when we get back from break. And MapReduce is kind of different than a traditional programming techniques. But if you guys are able to think about decorators and you're able to think about higher order functions, then you should be able to breeze through it pretty easily. So the first thing that I want to show you guys is the map function. And map is not a func_tools function, it's just a built-in Python library function. You always have access to it. What does map do? Map lets you call a function on each of the items in some iterable. So here I'm creating a list of numbers. Here I'm calling map with this function. I hope you all remember lambda functions, but this is just another way to define a function. It's basically f of x is going to be equal to x squared. So it's going to square the number that gets passed to it. And map is going to take this function and apply it to each of the values in some numbers. So when I run this, you will see that, hang on, let's just quickly. So here is our original list of numbers. This is the result of the map call. We took each number and we squared it. We can also, we aren't restricted to just lambda functions. We can use any function that we've defined. So here I'm calling the Fibonacci function from before. And you can see that we get the Fibonacci numbers. 0, 1, 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, so on. The trick is that you guys probably shouldn't be using the map function. In fact, it's pretty rare that you should be using the map function. For the most part, you should just be using list comprehension. These two statements are effectively the same. In both cases, we're iterating over our numbers, and we're calling fib on each item in the list. So this map is basically giving you the same power as a list comprehension. And you can see that they're the same because they have exactly the same result. Any questions on the map function? So, sorry, just to go back a second. Even though you shouldn't really be using the map function when you're working in Python, in a lot of other languages that don't have list comprehension, the map function is basically all you got, and it's what you use. That includes with some of the databases we're going to be working with. So yeah, I'm showing it to you guys now as a prequel. Any questions on the map function?
No.
Cool. Reduce is a little more complicated. Reduce is basically going to let you take a function that is going to, it's going to let you convert your iterables into some single value. It's going to let you do things like sum all the elements of a list or concat all the strings in a list. So, and the way it works, this is a quick implementation that I wrote up. And it's basically the same as the functools reduce function. I didn't say that earlier, sorry. The reduce function in Python can be found in the functools module. So we call functools.reduce. We have this kind of weird function, and we're passing it in a list of numbers. So what does this function do? This function is going to start building a result as it's moving through the list. And so this will be easier if I just said initializer equals 0. The first time you call it, A is going to be equal to your initializer, which is 0. B is going to be the first item in the list. The result of this function gets passed to this function call for the next item as A. So really quickly, fine. Is that how it works? Yeah. All right. So basically, what we're doing is summing all the elements in a list. So instead of using some specialized function like sum, I can use functools.reduce to get the same functionality with this specific function. This is going to take all the elements in the list and sum them up. So yeah. So how does this really work? Well, it can help to read this, which is basically an implementation of reduce. We have some function that we're going to be calling. We have some iterable that we're going to be iterating over. And we have a default value. If the default value isn't present, then our default value becomes the first item in the iterable. Otherwise, it becomes whatever our first value is. And then what we do is, so we have this value that's keeping track of something as we're iterating through the list. And for each item in the list, we update value to be the result of calling function on the value and the element in the list. And the final thing that we do is return the value that we computed. This is just one final example using the reduce, which is going to compute the average of some list. And this works by saying, I'm going to start with the object I'm collecting over. I'm going to be passing in an item as well. The collector is a triple, a 3-length tuple, keeping track of my average, my running total, and how many items I have. We then look at the item and we add it to our total, and we add 1 to our count because we've found one more item. The last thing that we do is update the average, and then we return the entire triple so that we can do it again for the next item. So here we call reduce. We pass in this reduction function. We pass in our iterable, which is range 5. And we're going to initialize it with a triple containing 0, 0, 0. We start with an average of 0, we start with a total of 0, and we start with a count of 0. And it will correctly compute that the average of over range 5 is 2.0. And I can verify that by calling the average function from all those cells ago. What's the issue? Fair enough. Fair enough. There we go. The average is 2. So I know reduce can look really complicated. It is, and for the most part, it's not recommended that you use the reduce function when you're working in Python. But it's part of the functools module, which is why I wanted to introduce it to you guys tonight. And in other languages and with other tools that you guys will be working with, the MapReduce framework is favored, and it's recommended that you use it. Conceptually, anything you ever do in a for loop can be done in MapReduce. Anything you have ever done in a for loop can be done with MapReduce. They're equivalent in power. And it's just a question of what style of programming you prefer. This is really just meant as a quick introduction. It's okay if this wasn't entirely clear. We're going to be getting to it in more detail as we move through the course. Does anyone have any questions on MapReduce or either map or reduce rather?
No, but I appreciate the overview.
Cool. Does anyone have any questions unrelated to any of the content I've covered tonight?
Hey Nolan, I'd like to go through the starting part about the decorators things. I think I need to spend some more time on that thing, and then if I have any questions, I will let you know. No, I mean, I'll let you know later. I mean, not now. I mean.
Oh, well,
Yeah.
okay.
Yeah, sure.
The major takeaway is just to understand that a decorator is a function that accepts a function as an argument and returns a function, and that this syntax is exactly equivalent to this syntax. This is how it works. It's just calling a function. It's a pretty way to do it. Conceptually, decorators let you add functionality to existing functions. So instead of having to define a new version, so for example, instead of having to define a new logging version of every function in your just everything, you can define this one decorator that implements logging functionality, and you can just throw that on all of your functions that you want to log. It lets you add functionality without having to change your source code, basically.
Got it. Yeah.
Any other questions by anyone? I can't tell if I covered this all really well and there's just no questions because I covered it really well, or if I covered it poorly and you guys can't figure out how to phrase your questions.
For me, I think you covered it really well. I just need to go back over it to get it into my head. But I'm really pleased with how you explained.
Sure. All right.
Yeah,
Well,
thanks a lot, Nolan. Very sweet of you of taking the time.
To watch a couple videos on this to understand it.
Sure. Yeah. I wouldn't be overly concerned about understanding MapReduce. Once again, the only reason I showed you that is because it's part of the FuncTools library, which I was using a lot of for decorators. Like, whenever you're creating a decorator, you really should use functools.wraps. You just should do it. It will make your life much easier. But
it is helpful when you explain this other stuff. Anyway, it just sort of helps me understand the way it thinks.
Yeah, that's the hope. All right, well, unless there's any other questions, I think I'm going to log off.
Thanks, Nolan.
Thanks a lot, Nolan. Very sweet of you.
Yeah, thanks, Nolan. Yeah, FuncTools is really good. I think I really want to look into it, and it seems really useful. Thank you.
All right, well, good evening.
Yeah, good evening.
Take care, see you all tomorrow.
Bye.
See you guys tomorrow.
See you guys tomorrow.
Ciao.